Okay, well, welcome everyone. This is the first talk for this semester in TCS Plus, so we're really excited to have Sophie Huiberts today from CNRS and LIMOS, is that how you pronounce it?
Yes.
Who will tell us about some upcoming work at Stock, analyzing the Simplex method by the book. So before I hand it over to Sophie, I do want to say a few words about TCS Plus. So TCS Plus is this long-running online seminar where we invite people from all over the world to talk about recent or even not so recent results in theoretical computer science. It's been running for now over 13 years, I believe, and so we can always use people's suggestions to for what you think would be a great TCS Plus talk. Please go to our website and submit your recommendations. Now, for today's talk, I really want to encourage everyone to keep their cameras on. I know that from personal experience, it's much nicer to give online talk where you can get some kind of visual feedback, and you should feel free to unmute yourself if you have any questions. And there will also be an unrecorded session with Sophie right after, so you can stick around and discuss anything that comes up. And finally, before I hand it over, let me thank the rest of the TCS Plus team. This includes Clement Canon, Rachel Cummings, Sumega Garg, Shivam Nanampali, and Yasmin Nazari. All right, so with that, let me hand over the floor to Sophie, and please take it away.
Thank you, Eric. Thank you for the introduction. Thanks for having me, and thanks all for being here. Yeah, so this is some new work that I'm very excited about. It's joint work with my PhD student Elian Bach, as well as with Alex Black and Sean Kafer. And yeah, so let's just get started. So we're solving linear programs. I'm gonna assume that everybody roughly knows what a linear program is, but let's go through it just to like get our definitions in place. We are gonna be given a matrix A, a vector B, and a vector C. And what we're going to do is we're going to solve the linear program, maximize C transpose X, subject to AX at most B, X non-negative. So here, these two inequalities, AX at most B, X non-negative, are coordinate-wise inequalities. So we have a system of n linear inequalities in the ax most b, and then another d more inequalities x non-negative. We have x is a vector of length d. D is for dimension. This is how many dimensions we're having. And in this problem, it is our task to, first of all, find out if there is an x such that all of these inequalities are satisfied simultaneously. And if so, we want to find one of the x's for which the inner product C transpose X is maximal among all these satisfying feasible x's. For later purposes, let's assume without loss of generality that all of the rows of the matrix A have one norm equal to one. Now, in this program, we're going to solve it. We're going to look at the simplex method, which is arguably one of the most important algorithms we have for solving these linear programming problems. The way that the simplex method works is without loss of generality, we start out knowing some vertex of this feasible set. Note that the set of all the feasible x's together, they form a convex polyhedron. We know a vertex of this without loss of generality through some trickery. And what the simplex method is going to do is it is going to pivot along edges to neighboring vertices. And it will keep doing these steps. So in the image here, we are taking 3 so-called pivot steps until at some point we find an optimal solution. And this is like there is linear algebra backing all of this, but do not worry, you do not have to know that for any of that for the purpose of this talk. The thing that I'm going to be interested in is the thing that has honestly been the subject of most theory research into the simplex method, which is how many pivot steps are necessary for before the simplex method will find its optimal feasible solution. this is because the simplex method is such a practical algorithm. There is a lot of like practical wisdom about how fast this algorithm is. And everybody agrees that the simplex method runs in linear time. Linear in what exactly depends on who you ask, but everybody agrees that this is a linear time algorithm. Um, and it is sort of observed to be very linear. So like I write like, oh, it's at most 2 times n pivot steps. That is like it's a rule of thumb, but it's a very robust rule of thumb. Like I don't know if anybody's ever observed the simplex method requiring more than say 10n pivot steps. Like observing even 5 times this number is profoundly rare. Observing 10 times this number might have never happened in 80 years of experience. So that is our ground truth. That is what we hope to understand. And so people have done a lot of proving theorems about the simplex methods. But initially, all the theorems came out to saying that actually the simplex method is slow. So these are results that started with Klee and Minty, who found a construction that demonstrated that one variant of the simplex method requires exponential time in the worst case. And so by now we have a lot of variants for different variants of the simplex method. We have different variants of the theorem saying, oh, this variant requires exponential running time. So a lot of theorems saying simplex method is slow, which is of course not true. We know that it is fast, but the theorems say that it's slow. And so there's a bit of a tension here. So naturally, people have tried to prove theorems that go the right way, theorems that say actually simplex fast. And there is also a long and proud history of people doing exactly that. Here, sort of, you should think about like smooth analysis or like average case analysis type algorithms. So you say, oh, let's assume that my A, my B, and my C, I draw them from some nice probability distribution, and then I prove that in expectation, the simplex method or whatever simplex method I study is polynomially fast. It has a polynomial upper bound on the expected running time. But there is so like and sort of this second line of work, I spent many years doing this, and this is sort of was generally like very well appreciated research. But there's a problem, which is like if I say it nicely, I would say that all of these theorems don't give actionable insights. If I say it less nicely, I would say that the people who actually develop simplex methods, the people whose job it is to program a very fast simplex method, they don't like these theorems. They think that there is nothing in these theorems that they can learn anything from. Like they don't really respect this work because it's kind of trash. I know that there are some of these people in the audience. I hope I will. I hope that they agree with my characterization. Um, so this is kind of the deal that we're in. There's a lot of theorems, but none of them sort of really get to the core of what at least the practitioners think is accurate about all of these things. And that's kind of what with this project we set out to change. And so we thought about it for a while and we thought, well, what makes for a good science, right? Like sort of because this is fundamentally is a scientific question. We have observations and we want to have a theoretical framework that would explain these observations. And then we concluded that all the real sciences require observation. This is so like I'm very envious of physicists because physics is in a sense it is the science among sciences, and they have it figured out, right? They have theories, they have observations, they can do experiments to test their theories, and it all works out very well. In exactly the picture perfect image that we have of what science should be. And that is, I kind of, we wanted to replicate some of that. Um, so that is what we set out to do. We started out observing simplex methods. So we dove into the scientific literature. We downloaded user manuals for many different linear programming software packages. We read source codes of open source solvers. We did interviews with developers, and we looked at some data sets of like linear programs, and we made up a large pile of observations, things that we thought were should be theoretically relevant. And what we then did is we out of those observations we derived some assumptions, and with the assumptions we can prove theorems. And that sort of so this is what we call our by the book analysis framework. Roughly speaking, sort of think of it as if you want to prove a theorem about an algorithm and you want extra assumptions, that's fine. You can make any assumption that you want, so long as you have rigorous observations to back them up. This is an observation first mathematical theorem proving game. Now, of course, this is not always like a super linear thing because in the end, sort of we had our proof and our proof suggested that actually we should try and measure this specific property of our data sets. And so we did sort of after we'd gone down, we went back to our observations and tuned it all a bit more. But really think of this as like a linear flow from top to bottom. And hopefully this way of operating will produce better results, more actionable theorems. That's the dream. And so what we found throughout this whole process is that actually I lied to you already on page 1, because the way that we classically think about the simplex method as, oh, we have a convex polyhedron and we move from vertex to vertex, blah, blah, blah. That's fake. That's fake. Like none of that geometry really exists. And of course, you know that the geometry doesn't exist because the computer, it doesn't do geometry. It has floating point numbers. And we hope that those floating point numbers represent something. But there's also a more fundamental thing to this, where this geometry really is fake and doesn't exist. And they are actively the software people, they're actively working to make it not exist. And so they have like a number of techniques. I listed a couple of them: bound shifting, Harris's ratio tests, tolerances, perturbations. Like they have a whole bag of different tricks that all depend on this geometry being fake. And like whenever the geometry doesn't suit you, you can just shift around all the numbers to make it work. And so I mean, this is sort of it's hard to convey in generality, but really sort of what's important is that there is no sort of fixed geometry that we're operating on, and it's more the geometry can kind of change if you have a strong need for it.
So, Sophie?
And yeah.
Sorry, I just had a question. I mean, you're probably gonna get to this. Um, I was wondering, like, when you are saying like the theory with actionable insights, is this gonna be like you're gonna change the algorithms, or you're gonna give some explanatory power for this like 2n pivot steps, or
I mean
maybe I'm getting
that's the
myself.
goal, right? Sort of so the ideal goal to me sort of like we're analyzing an algorithm, and to me sort of an analysis that should teach you something about how it works. And what to me would be an ideal sort of set of theorems is you have both a proof that under these circumstances it's fast, but also these circumstances are actually true, sort of like measurably true. And you might even want out of a theory to say that, oh, in the theory, like theoretically speaking, progress happens if this happens, and progress is big if this number is big, progress is small if this number is small, or something like that. And then you could actually go into your computer and you could actually observe that number be big or that number be small, and have it sort of have the judgments that you get from the theorems line up with the judgment in practice. Or like, so if you want like insight into, like, you want to be able to observe more closely what is happening and see, can I learn anything about that, and can that inform changes to the implementation? Because to me, like, that really is sort of the important insight, that what your classic sort of the way that you learn the simplex method from a textbook Like there are a number of things that are just not true. So if you gotta when you implement the simplex method, there are a number of changes you have to make. Everybody makes the exact same handful of changes, like sort of basically what you have on the slide here. There's like 5 changes here, sort of under numerical linear algebra. You have 5 changes. Every good solver in the world has the same 5 changes, because otherwise your simplex method either doesn't work or is very slow. And so, presumably, if everybody agrees that these are the 5 good things that you should do, a theory has to have them as well. If your theory does need them, but practice does need them, then clearly it is the theory that is not giving us insights. And so that really is, I would say, sort of what we want to do with this sort of by the book framework. We want to take sort of these differences, these important differences that everybody agrees are good, and we want to prove for at least some of them that they are good, not just in practice, but also in theory. To me, that is really the goal. Yeah, thanks for the question. Um, so let's discuss what I think are some of like, or let's discuss sort of the differences that we managed to theorize about. Um, the first one that is important and that we could actually do something are tolerances. So what you got to realize is that when you give a linear program like, oh yes, ax at most b x non-negative, the software will not always output an X that exactly satisfies these constraints. Instead, the software is allowed a small tolerance. If it can output an X, and so long as AX is less than or equal to B plus the tolerance, and if X is, well, not non-negative, but at least greater than minus the tolerance, then it's fine. It is still considered feasible. And similarly, sort of for the certificate of optimality, Y star, the dual solution, also sort of any inequalities that you have, you are actually allowed uh, to relax by the tolerance. And the only thing that the software promises is that if a point satisfies the constraints exactly, then the solver will call this a feasible solution. If a point violates a constraint by more than the tolerance, the software will recognize that this is not a feasible solution. But anything in this gray area, the solver can choose itself, whatever it likes, whatever it sees fit. And this is like you can open the Gurobi user manual, the Simplex user manual, or the FICO user manual. They all do this. And they all agree that the tolerance, both the feasibility tolerance and the optimality tolerance, they are 10 to the minus 6 by default, but you can increase them to as high as 10 to the minus 4 or decrease them to as low as 10 to the minus 8. But imagine like 1 in a million as the tolerance, and that is an absolute quantity. All solvers, like all production solvers do this. There are some exact solvers that are like really made for mathematicians doing like proofs and who need like exactness. But if you look at like what is just happening in actual industry, people who are actually solving linear programs for a living, they all allow this tolerance. And the user manual informs you about it. This is broadly agreed on. So yeah, so we have like our primal feasibility, we have dual feasibility, and then to sort of certify that your solution is optimal, you need to have like a complementary slackness condition or something of the like. And there are ways of incorporating the tolerances in all of them. Yeah. So that is, to me, that is perhaps the most important difference. And this difference has a natural cause because so what happens is that when you have like a 64-bit floating point number, it has a relative accuracy of 10 to the minus 16 because you have like what is it, like 52 bits of decimal, no, of binary digits, which is like 16 bits of decimal digits. So that is the accuracy of your numbers. And then but then you need to solve systems of linear equations. And when you do that, you might lose up to 10 significant figures. Again, this is the user manual will tell you, please make sure that whenever you solve a system of linear equalities, you lose no more than 10 significant figures. That is an instruction to the user. Everybody agrees that this is the instruction the user is given. And so 10 to the minus 16 times 10 to the 10 is the 10 to the minus 6. So there is, these numbers don't exactly come out of nowhere. And so in that sense, these tolerances are necessary. But I think that the place where this gets interesting is that as soon as you allow yourself a bit of room to fudge the numbers, then of course, like programmers, they are very smart people. So they will actually, whenever you give them any leeway to do anything, they will exploit it and they will make their software faster so long as they stay within these tolerances. So that is the goal. And one of the tricks that they do that where they use these tolerances to grow faster is by just changing their right-hand side. So we have a right-hand side and we have a lower bound, x at most b and x non-negative. And both of these sort of vectors, the zero vector and the b vector, one thing that the software can do is before it does anything, before the simplex method runs or anything happens, you just change these numbers at random. You make the feasible set slightly larger by a random quantity. Like here is I'm adding these epsilons, and these epsilons are uniform distributed between 0 and 10 to the minus 6. If you go on GitHub and you look up the source code of Highs, the fastest open source MIP solver that there is, you can see them do this. Everybody agrees you gotta do the perturbations. Although like specifics might vary by solver, and like there's some people do it always in the primal and sometimes in the dual, or no, I think the other way around. Always in the dual, sometimes in the primal. There's things I'm not gonna dive into, but everybody has some variant of these perturbations. And in our theorem, in our paper, we also decided, okay, so clearly perturbations help in practice, so they gotta help in theory. And so what we did is we made up in our own algorithm, we add perturbations as well, but now like instead of doing them uniform, we have some wacky probability density function and whatnot. This is boring mathematics, not the part that I actually want to get into. But I think the thing that's interesting is that yes, like there are, you can look at this and you can come up with ways of like mathematically formalizing them with small adaptations, and then you get something out that maybe you can prove theorems with, and you can actually prove theorems with. Now, so this is an assumption about the small scale, and the general principle about anything geometric is that when you have a small scale assumption, you need a large scale assumption as well. And there are a lot of large scale assumptions that you can read about in the user manuals. So the user manual, when you want to solve LPs in real life, the user manual tells you a lot of things. It tells you that for every basis, for every square submatrix of your constraint matrix, you need to make sure that the condition number is at most 10 to the 10. I'm going to call it kappa here. So this is the 10 to the 10 that I mentioned before. Like when you solve a linear system, you lose at most 10 decimal digits of accuracy. User manual tells you, please make sure that this is true. User manual also asks you that your constraint matrix A, all of the numbers should be either exactly 0 or order 1, which in Highs at least is operationalized as saying we want it to be between 0.1 and 20, or negative 20 and negative 0.1. And if this is not true, then the software doesn't trust you, and it might try to rescale your rows and your columns to make it true. But like if you behave nicely, if you are a good user, you will make sure that this already holds in exactly the way how you wrote down your linear program. And then there is also some more qualitative advice, which is that they say, oh, whenever you have any number, please make sure that you specify it in the appropriate units. So when you're gonna, I don't know, when you need to purchase sand, you know, are you gonna measure it by grains or are you gonna measure it by megatons? And sort of because like as the modeler, you probably already kind of know what the answer is going to be, at least order of magnitude. So make sure that you choose your units so that in the optimal solution, every number that is going to be in there is either going to be 0 or order 1. Probably sort of you can probably think of it as again like between 0.1 and 20, let's say. Um, so this is all user manual advice. Um, So this is the large scale. Um, we also in the paper we have some assumptions on the large scale, but of course we need something a bit more rigorous. So what we decided to look at is a quantity called the mean width, and this is comes from theory of convex bodies, where if I give you a convex set, you can calculate the mean width as follows. You select, you sample a uniformly random unit vector. You maximize this vector, you minimize this vector, and you take the difference between it. So what is the width in a direction? It is sort of just like whatever is the smallest slab that your body fits in within, like for a slab oriented in this direction. And it's the mean width because we take the mean over all of the different directions. Like classic sort of Brun-Minkowski theory, convex geometers, they love this kind of shit. Um, and there are sort of like it satisfies a lot of sort of the properties that you want. Like this is really a size measure in the sense that if I have a larger convex body, then the mean width will be larger. You can, for some simple bodies, you can calculate almost pretty much exactly what it is. Like if you have an axis aligned box, you can calculate exactly what the mean width is. And the idea that we had is that hopefully if a linear program is well scaled, if it is appropriately formulated, then it should have small mean width. One sort of notable thing here that is definitely a big assumption that we're making is that this only works if your convex body is bounded. Because if your convex set is unbounded in some direction, then the mean width will be infinite. So this is a measure that is only like properly defined for compact sets, for compact convex sets. Now, so I mean it's all nice and well to claim it, but we actually did a measurement. So what I did is I downloaded a data set of 240 real life linear programs, or I don't know if they're real life. This is the classic benchmark set called MIPLib. It's a set of like 240 MIPS. You can download them. And so for all of these mixed integer programs, I took the LP relaxation and I tried to measure what is the mean width. I sampled random objectives, I maximized, I minimized, I looked at the difference. And what I found is that so here sort of like I have a little table with results. I have like the mean that I measured and the maximum width that I measured among my 100 samples. And so like some problems were unbounded, but among the ones that were bounded, you can see that these are very respectable numbers. Like the vast majority are sort of like it's almost a majority that have a mean width smaller than 100, and like a vast majority that have a mean width of less than like 10,000. And I need to stress that this was a surprising result. Sort of like the fact that the mean width is bounded at all is not obvious because imagine that you have like our axis aligned box. Like if you have like a unit cube, the I think that for a unit cube, the mean width would be way larger than what we actually measured here for the same number of variables. So this really is a quantity that apparently is small for real linear programs, at least sort of for like two-thirds, for like two-thirds, three-fifths of the measurements. Um, so yeah, so that is the mean width. And that is like I think our like last big assumption that we needed to make. And then um I guess there is a result. So this is the theorem that we actually end up proving, which is we have a simplex method that does these perturbations of the bounds and the right-hand sides that can solve the linear program up to the tolerances that we allow ourselves using a bounded amount of time. Um, where sort of, yeah, the bound is expressed in the number of dimensions, the mean width m of like the slightly enlarged, like, I mean, the way that these things go with linear programs, you never, you always need your auxiliary linear programs and everything, but like there's a mean width term, there's a feasibility tolerance term, there's a logarithmic dependence on the condition numbers. Um, but yeah, so really what this is saying is that yes, if your mean width is respectable and if you allow yourself a small error in feasibility tolerance, optimality tolerance, then the simplex method with your bound perturbations is provably fast. And we were very happy about this because sort of yeah, I mean like to because to me at least these are not like major assumptions, right? Like the feasibility tolerance and the presence of these bound perturbations, you can read that in the user manual, you can see it in the source code. Um, and so sort of I mean you can argue like quantitatively whether the bound is still too large, but at least qualitatively I think this is I'm very happy about this.
Well, sorry, Sophie, qualitatively, you're okay paying a one over like a polynomial dependence on the feasible tolerance?
Yeah,
Uh,
yeah. Um, because sort of like so the thing is like this is actually like a relevant thing here. That's um like if you sort of how do I say this? Like solving linear programs up to lower accuracy is known to be easier. So sort of, I mean, often, like traditionally, we often pose ourselves the question, oh, is the simplex method efficient in the worst case if you solve exactly? But I would say that there, in a very real sense, that is not the thing that we have empirical evidence for. Sort of like the empirical fact that we're looking to explain is how efficient is it to solve linear programs up to accuracy 10 to the minus 6. And sort of like square root of 1 over 10 to the minus 6 is to me it's not a very large number. So like poly dependence is fine. Um, yeah.
okay, yeah, yeah, that makes sense. Yeah, thanks.
Let's see. Oh, we're doing quite well on time. So I can say a bit about what sort of just like on a bit more technical level has sort of went into this on like a proof side because we are kind of a proof-based crowd here. And then afterwards I will say a bit more about like the pros and cons, about sort of like the scientific value. Did we miss anything? What are sort of the major qualitative issues that you can have with what we did? So first of all, uh, the simplex method, it has all of these different variants. And one sort of axis of variation is in the pivot rule that you choose, sort of in the geometry. I mean, we still talk about the geometry, even though it's fake. The pivot rule decides which of the outgoing edges is the one that you will traverse along. And the one that we specifically need to use for our analysis is the same It's kind of the same as has been the one used in all average case style and smooth analysis style results. It's called the shadow vertex method, or for us, the semi-random shadow vertex method. Um, Works like this. So we have our A, our B, and our C are given to us. We sample a unit vector theta at random. And now what we're going to look at is the path of those vertices that maximize some linear combination, some positive combination of theta and c. So we want to maximize theta plus c times c, transpose x, subject to our usual constraints with our perturbed b and our perturbed lower bound L. Now, sort of there is a lot of like uh, busy work necessary to make this work, but sort of the important thing to realize here is that this is a pivot rule in the sense that the set of maximizing vertices for this linear range of linear programs is a simplex path. Sort of like you have a number of different vertices that are different maximizers, and they are actually connected by edges, and they are like a walk on the feasible set. And so this is a rule that you can make work, and it is monotonically increasing and everything like that. So that is the pivot rule that we need. Um, and then I guess sort of like the other main ingredient that we have is our perturbations, right? Like we have sort of a random algorithm that is random in two places. We sample our random theta and we sample these random perturbations. And it turns out that if you sample your BIs and your lower bounds I's with some PDF, then you can prove that for any solution X, either X is super unlikely to be feasible, in which case that's fine because you're probably not going to visit it. It's probably not going to count towards your running time. Or you can prove that like all of the slacks are big. Does everybody know what slacks are? Maybe this is jargon. If it's jargon, then I'm sorry. I will not be able to explain what it is. But sort of you can sort of prove that like, oh yes, if you have an inequality like ax at most b, then the sort of the difference between the ax and the b is probably not tiny. That is the slack. Like how far away is your inequality from being tight or from being violated, let's say. And so you can prove things about that. Um, and then sort of, I mean, this is like it's a long argument. So like this is the last I will say about it. What you are in the end able to argue with plenty of legwork is that if you follow this pivot rule, then during your pivots in every step you will increase your t because sort of the maximum number t that your current vertex is optimal for, it increases. And what you can prove is that for most of the pivot steps, either they make primal progress in the sense that there is an edge that you travel along that is a long edge. So you traverse a lot of just distance in the feasible space, which can happen only a bounded number of times, or there is a dual progress. I don't know, probably this slide was not necessary because even I struggle to understand it. If you have any questions, honestly, uh, ask Elion, my PhD student. They actually know how all of this works. But yeah, anyway, every pivot step, either it makes primal progress or it makes dual progress. There's only a bounded number of times that each can happen, and at some point you have an upper bound on the running time. Um, Now, let's actually end with some of the more interesting stuff because as much as I think that our new approach is a lot better than all of this smooth analysis nonsense of the past, there are still a lot of ways in which there are sort of qualitative ways to improve. For one, in our analysis, we have used like we needed a very specific pivot rule, this semi-random shadow vertex pivot rule, and it's bad If you ask people, if you ask developers, they will tell you that it's bad. And so that's upsetting, right? Like, why can we only analyze something that is not good instead of something that is good? Clearly, this is a lack of theory because in practice they tried this, it's bad. Um, Similarly, their ratio tests. This is everybody agrees that the classic Danzig ratio test is garbage, and you should use the more sophisticated Harris ratio test instead. Our analysis, we cannot use the fancy ratio test. We can only use the shitty ratio test. That is, again, a thing that is bad about the theory because the practitioners agree that the bad thing is bad and the good thing is good. So the fact that the theory cannot show that the good thing is good, that is, I want to change that, but it'll be difficult. Um, s- uh, like I don't know, like there's a lot of sort of qualitative things that you can say about this because we had our assumption about the mean width that we want sort of the theorem says if the mean width is small, then algorithm fast. But there are sort of like this is a thing that you can kind of test, right? You can sort of do a lot of transformations to the programs that are known to make the algorithm fast, and you can ask, oh, are they also making the mean width smaller? Because if the theorem says these two numbers are related, then surely in practice you could measure both numbers and see if they are related. We don't know. Nobody's done this yet, but it would be good because I think to me it's like if a theorem proposes that numbers A and B are related to each other, then you should be able to measure it and see that they're related. Otherwise, the theorem is lying to you. Um, Important work has yet to be done. Um, Then there is a big topic about the dual simplex method. Because so far I've only been talking about the primal simplex method, where we solve the primal program. For the dual, this is very much more difficult. For one, all of our theorems don't apply to the dual because the dual linear program is unbounded. And what I said about the mean width, it is only defined for a bounded feasible set. Um, other cool techniques that they do in practice. Yeah, I don't know. There's a large bucket of different techniques and stuff. These software people, they have so many smart ideas, and I just want to make theorems out of all of it, but we don't know yet how. That's it. Thanks.
Okay, we can pause here a few minutes for questions, or we can also go to the unrecorded session. Okay, or is there Magnus? Yeah, go ahead and you can unmute yourself.
Yeah, I just gonna verifying how informal or formal you were, something said earlier on. But if you take one of those constructions that theoretically has exponential convergence time and you run it on a real solver, you're saying that the roundings and so on, your claim about like 2D iterations holds even for that?
Yes, yes. This is so like this is like a on the level of a fun exercise. If you program your own simplex method with your own known pivot rule and you feed it the Klemente cube for that corresponding pivot rule, it is very hard to get more than like 4,000 pivot steps. I think like when I tried this, I couldn't get more than 4,000 pivot steps. So which like 4,000 that happens at like 12 variables. So already for 13 variables, I couldn't get the predicted number of pivot steps anymore. So that is kind of how you should think about it. Like it's yeah, sure. Like there is an exponential curve that happens for a bit, but like a 12 variable linear program that is tiny, right? Like a real linear programs, they like a small linear program today is 1,000 variables. So sort of like anything that happens at like the sub 20 scale is not worth mentioning.
Okay, I'm just curious. I'm not an expert here in any way. Does that mean that many of these constructions are kind of in practice not solved because of the tolerance issues or something else?
Um, I mean, like they're like fundamentally, of course, not interesting constructions. So like of course nobody is like trying to solve them. Though I don't know what else sort of what is there to say about it. So
No, I would just think on the level of if you're teaching undergrads, I would always have been saying if I was teaching this stuff that theoretically speaking we can come up with constructions where these methods are very slow, but in practice they're not slow. And now I'm learning we can't even do that theoretically, so to speak.
yeah, yeah, sort of like even like yeah, exactly. It's like so sort of the way that you should understand this is that like it like this doesn't even necessarily have to do with like any of this intentional machinery, and it's more to do with the fact that when you have one of these worst case constructions, sort of if you want the worst case behavior to function, you gotta make the right pivot choice in every step. And by the right one, of course, I mean the wrong one. And there is only one wrong one. And the problem is that it comes down to like our 6 digits of accuracy because at some point we need to solve a linear system. We can only solve it up to 6 significant figures. And so as soon as the difference between the worst decision and the second worst decision is less than 10 to the minus 6, then probably due to like this numerical error, you're going to make the wrong choice, which is going to speed up your algorithm. Yeah, so in that sense, they really don't work in practice, even these theoretical constructions.
Thanks.
Do you have any lower bounds for like if you take these theorems like to the extreme, like can you build um or
So in this theorem, we have sort of this square root m over feasibility tolerance. And this is tight in a certain respect. Like if you allow yourself to use exponentially many constraints, like if n is 1 over the tolerance to the power d or something, then this sort of this square root 1 over tolerance dependence is tight. You cannot improve over it. Um, Now, of course, that doesn't mean necessarily mean that it's also like not improvable in the small n regime, because in practice, like n and d are of similar size. Like if you have 10 times more inequalities and variables, that is already a lot. Um, and so there it is unclear if you can improve it, but at least if you allow any number of constraints, then this theorem is tight.
okay, why don't I take us to the unrecorded session? And